Good afternoon, Sanchi nerds. You're watching Sanchineering. Okay, we're gonna just continue with some more hydrostatic stuff. So last time we talked a little bit about pressure, right? Pressure equals nothing other than force over area. So let's say we have a closed system of a piston with some gas molecules inside, and depending on depending on the moles inside the system, remember from ideal gas law, PV equals nRT, but we're going to focus on just as a function of height. So the piston can change height, and last time we derived the relationship as rho GH. So let's talk about these units real quick. A Pascal is defined as the unit of pressure from the brilliant scientist Blaise Pascal, the same as these units. So density is going to be, let's do SI units, kilograms per meter cubed, times meters per second squared, times height. And if you can see, we can cancel out kilograms. We can cancel out these 2 meters squared, and that would be, so we can simplify these units a little bit. A Newton is nothing other than a kilogram per meter per, no, kilogram times meter per second squared divided by meter squared. And this will be kilograms times meter squared per meter cubed times second squared. And as you can see, I can cancel out this meter with this meter to be left with kilograms per meter per second squared. And these 2 meters with these 3 meters to be indeed left with the same exact units, kilograms per meter per second squared. So it's important to understand this intuition, because when we deal with actual values, plugging in these numbers will make a little bit more intuitive sense if you understand the units. Okay, and the important thing to remember is that pressure is related to height, gravity, and density, okay? And it's also related to force. Remember that force is a vector, right? It has magnitude and direction, so you can draw a force arrow, okay? But pressure, for one weird reason, pressure is a scalar, okay? This is a little bit counterintuitive because pressure and force are almost used interchangeably, but it's important to realize that pressure is a scalar, okay? So you can't draw pressure vectors. You can't do pressure pushing down. That, yes, the force of pressure is pushing down, but pressure itself is a scalar, okay? The one thing to remember, though, is that pressure is a function of height for a single fluid, and if you have multiple fluids, it's a function of both height and density, okay? There's multiple fluids in your system, okay? So those are some important things to remember that we'll probably go more into, but it's a little bit counterintuitive, and we'll see some examples of why this is so confusing, okay? Just think about in the ocean, right? Little side note. The pressure here should be the same as the pressure here, right? But if you go deep down, the pressure here is definitely going to be much less than the pressure here, okay? Think about that for a little bit. So it's a function of height. As height increases, pressure decreases. And it's linearly proportional because these are all just linear terms. There's no squares, there's no square roots, okay? Just think about that for a little bit and we'll do some examples, okay? And let's develop a little bit more intuition. So here I've drawn a little tank with some water, and basically we have an equation for pressure, okay? So if we do a force balance at the bottom of a tank, you're gonna sum up all the forces, and really we have gravity and all that stuff, but let's consider the force of pressure, okay? So the way we write this is we have the force of pressure due to the water right here. So if this is the height, that's this rho GH, but we also have to add what? The atmospheric pressure, okay? Okay, so the atmospheric pressure is going to be determining the total pressure at the system, okay? But what if you have a closed system, such as a tire, right? Have you ever measured your tire pressure? So you have like a barometer. Remember, barometers measure tire pressure. So it's important to understand that there's different types of pressure readings. Okay, you might have the absolute pressure, denoted as ABS. You might have the gauge pressure, PG. So this is the absolute pressure. And this is the gauge pressure. And as we just described, this is the atmospheric pressure, the pressure of the atmosphere. So if you ever work in a lab or you're doing a problem, it's important to distinguish the difference between these three. Okay. So some pressure sensors measure in terms of the absolute pressure, but most of them measure in terms of gauge pressure. And gauge pressure is in relation to the atmospheric pressure. Okay. Okay. So if the gauge pressure reads 1 atm, well, the total pressure in the system is actually going to be 1 atm plus the atmospheric pressure. Okay, so then we have this relation. The total pressure in the system is going to be the P gauge plus the atmospheric pressure. And this is going to be your absolute pressure. Okay, so you sum up the gauge pressure and the atmospheric pressure, that gives you the absolute pressure. The way to remember that is this is kind of like the total pressure, and this is the got him.
Got him!
Got him pressure, kind of. I don't know, that's kind of how I memorized it. I remember being kind of confused on how this makes sense, but it's just how barometers work, right? Okay, I hope this kind of makes sense. We'll put it to more useful practice problems later on, but just kind of try to keep all these things in the back of your mind, that there's a difference between gauge pressure and atmospheric pressure and absolute pressure, and a couple things about pressure in it of itself. Pressure is a scalar, while the pressure of force, the force of pressure is a vector. Okay, might be a little bit confusing, but we'll see it in some examples later on.